how to assist task designers in deploying tasks on crowdsourcing platforms. This is Dong Wei, a PhD student from Big Data Analytics Lab at NJIT. This is a collaborative work between myself, my advisor Sanjoti, and Fihim from CNRS. Crowdsourcing platforms such as AMT, Figure8, and Full Factory are gaining popularity to be used as a medium to deploy a variety of tasks that require human intelligence. These tasks range from simple ones, such as imaging tagging, character recognition, sentiment analysis, to more complex ones, such as collaborative editing, product design, or even software engineering. Requesters log into these platforms with tasks that are to be deployed and want to achieve certain accuracy, latency, and cost, and typically following the pipeline that consists of 4 high-level steps. First, strategy design, which is to figure out how many workers are needed, how to leverage the workforce, and in what fashion. Second, worker recruitment, which is hiring workers to complete the task. Third, following which workers complete the task, and fourth, the result produced by the workers need to be aggregated and validated. Currently, this process is entirely trial and error based, and no help is provided to the requesters in strategy design. So, what are the deployment strategies for a task? A strategy involves the interplay of multiple dimensions, such as structure, which is whether to solicit the workforce sequentially or simultaneously, or organization, which is to organize it collaboratively or independently, and style, which is to rely on crowd alone or on a combination of crowd and machine algorithms. As an example, as described in the figure, for the same English translation task, there could be different strategies to accomplish it. We summarize task deployment challenges in real-world platforms. First, as aforementioned, there exist many types of tasks, from simple ones to complex ones. Then, there is a static form designed, which allows task designers to specify her deployment parameters on cost, quality, and latency. But requesters are not given any information on available workforce and how to arrange them to accomplish the threshold. So our work is the first formal step towards that. Specifically, we make 3 contributions on this work. First, we describe how to express deployment strategies as a function of worker availability. Then, we formalize how to satisfy a set of incoming deployment requests by recommending corresponding strategies to the task designers and present a framework towards that. Last, we present principled algorithms for the framework and preliminary experimental results to demonstrate the effectiveness of our algorithm. This slide describes our first contribution, that is how to model deployment strategies. A deployment request D contains threshold on quality, cost, and latency, referred to D quality, D cost, and D latency. These are the deployment parameters of a request D. The first threshold is a lower bound, and the latter 2 are upper bounds. On the contrary, as we have discussed, a deployment strategy S is a choice of value for 3 dimensions: structure, organization, and style. Intuitively speaking, a strategy S is suitable to be recommended to a deployment request D if the estimated strategy parameters satisfy the deployment parameters. That is, as quality greater or equals to D quality, and as cost lower or equals to D cost, and as latency lower or equal to D latency. The modeling problem therefore involves estimating cost, quality, and latency parameters of each strategy S, which needs to account for worker availability and the type of tasks that are part of deployment D. A simple but reasonable approach to that is to first match task types in a deployment request with workers' skill to select a pool of workers. In that way, we estimate worker availability W for given D and S. After that, we express strategy parameters as linear functions of a worker availability. One such example is shown in the slide for strategy parameter quality, that is, for S quality, which is a linear function of worker availability of types of tasks that are part of deployment request D. This slide describes the proposed framework overall. Consider M deployment requests are submitted to the platform. Each deployment request D contains deployment parameters, a lower bound on quality, an upper bound on cost, and an upper bound on latency. Each platform also has a finite pool of available workforce who are qualified and ready to undertake the task part of deployment requests. We assume that worker availability W is known to the platform. These are the inputs to the aggregator module of the framework. This module consults with the batch deployment module to recommend multiple strategies to this batch of M requests. In this paper, our primary focus is to study the batch deployment module. Naturally, in certain cases, the platform may not have enough worker availability to satisfy all M requests. Therefore, the batch deployment module may not be able to satisfy all M requests as well. In that case, our goal is to satisfy at least a subset of requests. Selecting which subset is most important and is studied as constraint optimization problem considering two different objectives. One is by maximizing throughput, that is, maximize the size of the subset, and the other is the payoff, that is, maximize the aggregated payment that the platform will receive based on the selected subset. The constraint is designed on the worker availability W. These two variants are formally defined in the paper. The novelty of our problem formulation is that it is capable to incorporate any other objectives as well. Next, we describe our proposed solution at a high level. The solution consists of 6 different steps. Irrespective of the underlying goal, the first step is to calculate the workforce for M deployment requests. Since the framework intends to recommend multiple different strategies for each deployment, the step 2 of our solution is to compute aggregated workforce requirements per request. We consider 2 aggregation functions, sum and max. The details could be found in the paper. Now, not all of the requests can be satisfied due to the limited workforce. Therefore, in step 3, the objective function value of each deployment request is calculated. Step 4, 5, and 6 are the steps that are needed to select a subset to optimize a given goal. Step 5 is greedy in nature, which makes our solution efficient. In the last step, the algorithm makes a comparison based on the underlying goal and choose the one solution considering 2 cases, an already selected subset of requests or the next request. The one which has a higher objective values is chosen. This process is repeated until W is exceeded. We prove that the throughput maximization is polynomial time solvable and represent exact solution to the problem. On the contrary, we prove that the payoff maximization is computationally intractable. We prove that the decision version of the problem is NP-hard by reducing 0-1 knapsack problem to an instance of the payoff maximization problem. Our proposed solution achieves 1/2 approximation factor, and the proof is presented in the paper. The running time of both algorithms is same and efficient. Our preliminary experimental results are presented next. We synthetically simulate a deployment scenario considering 5 requests, 30 available strategies, and set the value of K to be 10. We also implement a baseline solution that sorts the strategies akin to step 4 of BatchStrat, but does not perform step 6 of the algorithm. Overall, there are 2 observations in the results. First, our solution BatchStrat returns the exact answer for throughput optimization, as we proved. Then, The approximation factor for payoff maximization is always above 0.9. To summarize, our work is designed to recommend strategies to multiple deployment requests, and our preliminary work opens up more than one research direction. First, how to estimate worker availability for different types of tasks is a challenging problem that requires deep investigation in its own merit. Then, the interesting open problem is to come up with principled yet practical models to establish the relationship between deployment parameters and the strategy parameters. Finally, if all incoming requests can be satisfied due to limited workforce, how will that be handled? These last two aspects are studied in our SIGMOD 2020 paper.